The engineer stood motionless beneath the wing, his hand resting against the aluminum skin. He did not speak. He did not move. He simply stood there measuring something that could not be measured with instruments. The others waited. They had been waiting for him to say something, anything that would make sense of what they were looking at. He said nothing. November 1944. Occupied Soviet territory, Eastern Front. The aircraft had come down 3 days earlier, damaged but largely intact. A navigational error, perhaps, mechanical failure. It did not matter. What mattered was that it was here, on the ground, accessible. A Boeing B-29 Superfortress, the most advanced bomber in the world. And for the first time, German engineers would have the opportunity to examine one completely. The excitement had been immediate. Intelligence officers had been requesting access to a captured B-29 for months. Rumors about its capabilities had circulated through technical briefings, through intercepted communications, through the accounts of Luftwaffe pilots who had encountered it over the Pacific. But rumors were insufficient. Germany needed specifications, measurements, evidence. A team was assembled within hours. Engineers from Focke-Wulf, Junkers, and Messerschmitt, metallurgists, propulsion specialists, men who had designed some of the most sophisticated aircraft in Europe. Men who understood what was possible and what was not. They arrived expecting to find innovations, clever solutions, design philosophies that could be adapted, studied, reverse engineered. They arrived with notebooks, cameras, and measuring tools. What they found was something else entirely. Not innovation, incompatibility. Germany had entered the war with confidence in its engineering capability. That confidence was not unfounded. German aircraft had introduced innovations that redefined aerial combat. The Messerschmitt Bf 109 had been one of the most effective fighters of the early war. The Focke-Wulf FW 190 had shocked Allied pilots with its performance. German jet technology was years ahead of anyone else. The Messerschmitt Me 262 was operational, while Allied jets were still experimental. German engineering culture prioritized precision. Every component was designed to exacting tolerances. Every system was optimized for performance. Efficiency was paramount. Weight was minimized. Complexity was accepted as the cost of superiority. This approach produced exceptional aircraft, but it also produced aircraft that were difficult to manufacture, resource-intensive, and challenging to maintain in field conditions. A single Bf 109 required thousands of man-hours to build, skilled labor, specialized tooling. Materials that were increasingly scarce as the war continued, but the philosophy held: quality over quantity, sophistication over simplicity, precision over scale. The B-29 represented a different philosophy entirely. American engineering had developed along a separate trajectory: standardization, modular design, ease of production. The goal was not to build the most sophisticated aircraft possible, but to build an aircraft that could be produced in vast numbers by a workforce that included workers with minimal specialized training. This difference was known, in theory. German intelligence had documented American production methods. The reports existed, but understanding a concept intellectually and confronting its physical manifestation are not the same thing. The B-29 was the physical manifestation. It was enormous. Wingspan of over 40 meters, length of 30 meters, weight exceeding 60 tons when fully loaded. It could carry 5 tons of bombs across a range of 5,000 kilometers. It could fly at altitudes above 10,000 meters, beyond the effective reach of most German fighters and anti-aircraft systems. But size alone was not the revelation. Germany had built large aircraft. The Focke-Wulf FW-200 Condor was a long-range bomber. The Junkers Ju-390 had been designed for intercontinental range. Size could be achieved. The revelation was in how the B-29 was built, and the quiet, growing recognition that Germany could not replicate it. The examination began with the airframe. The skin was aluminum as expected, but the thickness was wrong. Too thin, by German standards. German bombers used thicker aluminum to ensure structural integrity. The B-29's skin felt almost fragile in comparison. One engineer made a note. A design flaw, perhaps, an acceptable risk traded for weight savings. But as the inspection continued, the reasoning became clearer. The aluminum was thin because the structural load was distributed differently. The entire airframe was designed as a stressed skin structure, where the skin itself bore significant load rather than relying solely on an internal framework. This required extraordinary precision in manufacturing. Panels had to be formed to exact specifications. Riveting had to be flawless. Any imperfection would create weak points. It was an elegant solution. It reduced weight without sacrificing strength. But it required manufacturing capabilities that were, at that moment, beyond Germany's reach. German aircraft used heavier frameworks and thicker skins because German factories could not reliably produce the kind of precision panels the B-29 required at scale. Attempting to replicate the design would mean retooling entire production facilities, training thousands of workers in new techniques, securing aluminum supplies that were already critically short. The engineer made another note, not a flaw, a constraint. The engines were next. 4 Wright R-3350 duplex Cyclone radial engines, each producing over 2,000 horsepower, 18 cylinders per engine, turbo-supercharged for high-altitude performance. The power output was extraordinary, but the Germans had built powerful engines before. The Jumo 222 had been designed to produce similar power levels, but the Jumo 222 had never entered mass production. It was too complex, too prone to overheating, too difficult to manufacture with the materials available. It had been tested extensively, refined repeatedly, and ultimately abandoned. The R-3350 was operational, reliable enough for sustained missions, produced in quantities that allowed the United States to equip hundreds of B-29s. The difference was not in the design concept. It was in the ability to move from prototype to production. The German engineers understood this immediately. The engine was not revolutionary. It was achievable. What was revolutionary was that it had been achieved at scale and continued to function under operational stress. One of the metallurgists examined the turbine blades. High-temperature alloys, nickel-chromium steel likely. Germany had developed similar alloys, but the supply was limited. Strategic materials were allocated carefully. Jet engines received priority. Conventional engines made do with less. The B-29's engines used these advanced alloys liberally, not sparingly, not in critical components only, throughout the system. Because the Americans had access to raw materials in quantities that allowed for less conservative design choices, the notes accumulated, each observation adding to a picture that was becoming uncomfortable to articulate. The pressurized cabin was examined next. Cabin pressurization was not unknown. German engineers had experimented with it. The Junkers Ju 388 had a pressurized cockpit. But pressurizing an entire crew compartment, maintaining structural integrity at high altitude, managing the seals and airlocks, this was significantly more complex. The B-29 had 3 pressurized compartments: the forward cabin, the rear cabin, connected by a tunnel running over the bomb bay. Crew could move between compartments in flight, at altitude, in a combat environment. The engineering required to make this work reliably was staggering. Every seal had to be perfect. Every structural joint had to withstand differential pressure. The environmental control systems had to function continuously. Failure meant decompression, incapacitation, death. And yet the B-29 made it work, not experimentally, operationally. The Germans could have built a pressurized compartment. They had the theoretical knowledge. But building one that worked reliably, that could be produced in quantity, that could be maintained in field conditions with the resources available, that was a different challenge entirely. The inspection continued for hours, then days. Each system revealed the same pattern: sophisticated design, robust engineering, and an underlying assumption of abundant resources. But the full scope of the problem had not yet been articulated. The fire control system became the focal point of a deeper realization. The B-29 was equipped with a centralized fire control system, remote-controlled gun turrets, 4 turrets, each with paired .50 caliber machine guns, controlled by gunners using computing gun sights. The system could calculate lead deflection range. It could coordinate fire from multiple turrets against a single target. One engineer spent an entire day examining the gun sight mechanism. It was a mechanical analog computer. Gears, cams, gyroscopes. It accepted inputs for target speed, altitude, and angle. It output firing solutions in real time. Germany had developed similar systems. The Askania gun sight used in some German bombers was conceptually comparable, but the B-29 system was integrated across the entire aircraft, standardized, reliable enough to trust in combat. The engineer photographed every component, sketched the mechanisms, made notes on materials and tolerances. And then he wrote a single sentence in the margin of his notebook: "This requires an industrial base we do not have." The sentence was not dramatic, it was not defeatist, it was observational, a recognition that the gap was not in knowledge but in capacity. The pattern repeated across every system: the hydraulics, the electrical systems, the instrumentation. Each one was well designed, but each one assumed access to materials, manufacturing precision, and production scale that Germany could not match. The bomb bay was massive, designed to carry standard bomb loads in modular racks. The bombs themselves were standardized, interchangeable. Any bomber could carry any bomb. Any airfield could load any aircraft. The logistics were simplified by design. German bomb loads were less standardized. Different aircraft required different mounting systems. Ordnance varied by manufacturer. Supply chains were complicated by incompatibility. It was inefficient, but it was the result of a decentralized production system that had evolved over years of wartime improvisation. The Americans had avoided that trap, not through superior planning, but through the luxury of time and resources to implement standards before production scaled. The recurring element appeared in the margins of every report. The same phrase, written by different engineers in slightly different ways. Not impossible, impractical. It was a careful distinction. The engineers were not admitting that Germany lacked the technical knowledge to build a B-29. They were admitting that Germany lacked the industrial infrastructure to build it in meaningful numbers in the time available with the resources on hand. The B-29 was not just an aircraft. It was the product of an entire industrial system. And that system could not be replicated by copying the aircraft. The final report was compiled over 2 weeks. It was thorough, detailed, hundreds of pages. Photographs, diagrams, material analyses, performance estimates, every component documented, every system explained. And buried in the technical language, in the carefully neutral phrasing, was a conclusion that no one wanted to state directly. Germany could not build the B-29. Not because the design was beyond comprehension. The design was understood. The principles were clear. German engineers could, in theory, produce equivalent systems. They had the knowledge, they had the talent, but they did not have the industrial capacity. The B-29 required aluminum in quantities Germany could not allocate. It required high-temperature alloys that were in critically short supply. It required precision manufacturing at a scale that German factories, under constant bombing, could not sustain. It required a standardized production system that Germany had never fully implemented. It required time, and Germany had run out of time years earlier. The report did not say this explicitly. It did not need to. The numbers spoke plainly. To build a single B-29 equivalent would require resources that could instead produce dozens of fighters. Fighters that were desperately needed for defense. Fighters that could be built with existing tooling, existing supply chains, existing doctrine. The strategic calculus was unambiguous. Even if Germany could build a B-29, it should not. The resources would be better spent elsewhere. But the deeper realization was harder to quantify. It was not about a single aircraft. It was about what the aircraft represented. The B-29 was a demonstration of industrial capability so far beyond Germany's reach that comparison had become meaningless. The United States was not building better aircraft. It was building aircraft in a different category of scale. And that scale was not achievable through better engineering or superior design. It was achievable only through an industrial base that dwarfed Germany's. The same base that was producing tens of thousands of trucks, hundreds of ships, millions of tons of steel. The same base that had been untouched by bombing, unrestricted by resource shortages, and given years to mobilize before entering the war. The B-29 was not a weapon. It was a message, a physical statement of industrial superiority so overwhelming that no tactical response could bridge the gap. And the engineers, standing beneath that massive wing, understood the message perfectly. The question that followed was whether anything could have been done differently. The answer, examined honestly, was constrained by factors beyond engineering. Germany's industrial base had always been smaller than the combined Allied capacity. Geography limited access to raw materials. Strategic bombing had degraded production capability progressively throughout the war. Resources were divided between competing priorities: fighters, tanks, submarines, weapons. Even if Germany had recognized the importance of strategic bombing earlier, even if resources had been allocated to develop a heavy bomber fleet, the fundamental constraints would have remained. Aluminum was scarce. Fuel was limited. Skilled labor was finite. The B-29 required not just technical capability, but industrial redundancy. The ability to absorb losses and continue production. The ability to iterate designs without halting output. The ability to supply a fleet of bombers operating thousands of kilometers from home bases. Germany did not have that redundancy. Every loss mattered. Every resource allocation was a trade-off with immediate consequences. The industrial system was operating at maximum capacity with no margin for experimentation. The United States, by contrast, had margin, vast margin. It could afford to develop the B-29 over years. It could afford to solve technical problems through iteration rather than perfection. It could afford to produce the aircraft in numbers large enough to sustain losses and still maintain operational strength. The constraints were structural. They were not the result of poor decisions or lack of foresight. They were the result of entering a prolonged industrial war with insufficient industrial capacity. The engineers who examined the B-29 were not wrong in their assessments. The aircraft could not be replicated under the conditions that existed. The conclusion was not defeatism. It was realism. The captured B-29 was eventually destroyed to prevent its recapture. The reports were filed. The photographs were archived. The insights were disseminated to design teams, though by late 1944, the practical value was limited. But the story is not really about the B-29. It is about the moment when capability and capacity revealed themselves to be different things. Germany had the capability, the engineers, the knowledge, the technical sophistication to understand and even improve upon what they saw. But capability without capacity is a theoretical exercise. The war was not decided by who had the best engineers. It was decided by who had the most factories, the most raw materials, the most ability to absorb losses and continue production. The B-29 examination was one of many moments throughout the war where this truth became undeniable, but it was a particularly clear example because it removed the variables of tactics, strategy, and leadership. It reduced the question to pure industrial output, and in that reduction, the disparity became impossible to rationalize away. This is not a story about German engineering failure. German engineers accomplished extraordinary things under extraordinary constraints. The Me-262 jet fighter, the Type XXI submarine, the V-2 rocket, these were technical achievements that were, in some cases, ahead of Allied equivalents. But technical achievement does not win wars when the opponent can outproduce you by an order of magnitude. The lesson of the B-29 examination is not that Germany should have built better aircraft. It is that Germany was fighting a war that could not be won through engineering alone. Industrial wars are won by industrial capacity, and capacity, once the gap becomes large enough, cannot be closed by innovation. The engineers understood this. They understood it as they stood beneath that aircraft, measuring components that could not be replicated, examining systems that assumed resources Germany did not have. The silence in that moment was not confusion. It was recognition. So the question remains, if wars are ultimately decided by industrial capacity rather than tactical brilliance, what does that mean for how we study military history? And if the outcome was determined by factors beyond the battlefield, does that change the weight we assign to the decisions made by those who fought? This video is based on historical records, expert analysis, and documented sources. Some interpretations are simplified for storytelling clarity.